My name is Larry Hawkins, and I'm Director of Technical Marketing and Systems at Richardson RFPD. My presentation today is on software-defined radio design accelerators. Richardson RFPD is a worldwide distributor for RF and microwave components. If you're interested in getting a broad view on RF and microwave components available in the market today, please talk with one of our representatives. We cover components with frequency ranges from DC to 110 gigahertz and components from high-speed converters and DC power to antennas. Have you ever felt like the people in these pictures? The pressure seems to be increasing for engineers to get more done in less time with less help. Even with these increased pressures, it's still expected that things get done on time. Richardson RFPD has a wide range of design accelerators to help our customers get more done in less amount of time. Most of these accelerators were designed around analog devices parts, as they've done a good job at building out a portfolio of these type systems. But there are also many that are not designed by ADI. To be honest with you, even though most of these accelerators were designed for use in many applications and are applicable to many of our customers, we've not done a good job at highlighting them in the past. In this presentation, I'm only showing a portion of these due to the amount available and the diversity of our offering. The ones I will show fall into 5 categories. Even in these categories, there's a lot of diversity, and it's hard to express all the meaningful aspects of the design in a single sentence. My intention is to try and show you things that will help reduce the amount of time and risk associated with your design, not knowing what it is beforehand, and let you either dig a little deeper to find out more or contact Richardson RFPD for more information. The first category I list are platforms focused on highly integrated transceivers. These are based on ADI's high-performance, highly integrated transceivers and cover a wide RF frequency range. Some of them are in a very small SOM form factor and include the transceiver and a set FPGA. Others are in an FMC form factor and are flexible on what FPGA are used with them, and I'll be talking more about the bit pipe, highlighted in yellow, later on. But all of these are available to purchase from Richardson RFPD, and all of them could help decrease your design time. Accelerators that include FMC connectors are designed to allow your software and algorithm development teams to start their work, while the hardware team is tweaking the hardware for your application. They can be used to help demo your concept to a customer, or because the design files and hardware and HDL code is open source, you can also use them as a starting point for your design. Usually, these designs include HDL code for multiple FPGAs, making them flexible to match your team's FPGA experience and your design's needs. The SOMs are PC boards that include the RF transceiver, FPGA, shielding, heat sinks, RF connectors to interface to the transceiver, and a high-speed connector to interface to the FPGA. They're very small and can be evaluated using a breakout board that includes peripherals for things like Ethernet and USB connections. SOMs can be used to allow your software and algorithm development teams an early start on their developments. They can also be used to help demo your concept to a customer, but the form factor allows them to actually be used in your design. There's a large group of accelerators that focus on high-speed analog to digital converters. Some of these include discrete RF components that somewhat focus their applications. Depending on the perceived processing needs of the ADC, many include an FMC form factor, allowing them flexibility to connect to different FPGAs. Some of them use other form factors to connect to a processor of choice. Another grouping is high-speed digital to analog converters. This category includes a DDS-based vector signal generator and some DACs that have upconversion and frequency synthesis along with them. The last category has both high-speed DACs and ADCs for high-performance transceiver applications. These also tend to have an FMC connection to an FPGA of your choice. As you'll notice, most of the accelerators I've shown you are mainly market agnostic and can shorten your design time, and most also do not include a more market-specific RF front end. One of these design accelerators I thought I'd highlight is a SOM designed by NextGen RF. This SOM includes ADI's Navasa, or the ADRV 9002, and the Xilinx XCU3EG. It's very small and was made to be fully functional, or in other words, they've tried to allow you to use all of the ADRV 9002 features. This would include covering the full frequency range of the ADRV 9002, while the eval platforms break the frequency coverage into multiple boards, and its ability to be synchronized to other bit pipes or other systems. You'll note that it can be used for many applications, but needs an RF front end as it has limited output power on the transmit side and limited noise figure on the receive. You'll note that they did this specifically because if they were to include the RF front end on the SOM, it would most likely limit its applicability to some customers. Richardson RFPD has tried to augment these multi-application design accelerators with more market-specific RF front ends, and initially designed the DE705, 698 to 960 megahertz 5-watt output with LNA that will work with any 698 to 960 megahertz platform with DPD. Please note that the 5-watt output is at the connector and takes into account all the loss between the PA and the antenna connector. It also assumes an 8 dB peak to average ratio signal and a 50 dB ACPR. We show its performance along with the ADRV 9002 evaluation platform in a demo at our booth. Please visit us for more information. The DE705 can also be purchased with Analog Devices AD9375 evaluation platform. To go along with the DE705 and ADRV 9002 demo, we're also showing the BitPipe SOM with the FEA 445040, a 4.4 to 5 gigahertz 2-watt linear transmit output with receiver signal chain front-end design accelerator. The 2-watt output is assuming a 10 dB crest factor signal and a 50 dB ACPR. Please note that its output power could be a lot higher using a waveform with a smaller peak to average value. The noise figure listed is a system noise figure, not including the SOM, although the SOM shouldn't affect the system noise figure very much. When included with a BitPipe SOM, this design has everything from the antenna input to the FPGA, and not only lets the hardware engineers evaluate the performance of the design, but also allows the software and algorithm developers to start their design with the hardware engineers or NextGen RF tweak the hardware for a specific application. Another front-end design accelerator that will be available soon is the FEA 13527040. It's very similar to the previous one, but is tuned for a different band. In this case, it can be used between 1.35 and 2.7 gigahertz. A third platform that's being designed in parallel is the FEA 135-27020. This is a low-power version of the FEA 135-27040. Its 1 watt output also assumes a signal with a 10 dB peak to average value and a 50 dB ACPR. Similar to the other designs, the 1.5 dB noise figure is a system noise figure. Please note that these design accelerators can be used with any other design accelerators which work at its frequency and includes DPD. We're also in the process of designing a 24 to 44 gigahertz UpDown Converter design accelerator. This design accelerator is made to be used between an RF front end and an IF or baseband board. However, instrumentation customers may not need the RF front end. Because most people are using very wideband signals between 24 and 44 gigahertz, the up-down converter is designed for bandwidths of greater than 1 gigahertz. It's also designed to allow the customer to either use in direct conversion mode or an image reject IF mode. The design also includes the required filtering to have good performance over the full frequency range. Most customers will use this with a high-performance analog-to-digital converter and digital-to-analog converter because of their wide bandwidth requirements. Two compatible systems to the UDA240440 are the analog devices AD9081 and AD9082 eval platforms. Although I wouldn't define the eval platforms as design accelerators, many things can be copied from the design to reduce engineers' design effort. The ADS8 and ADS9 FPGA platforms can also interface to MATLAB for software and HDL development. Either of these eval platforms, whether combined with the UDA240440, allow engineers to get excellent performance for any attached RF front end. RFPD currently has partners that are designing 5G millimeter wave beamformers to be used with the AD908X and UDA240440 setup, and customers that are considering this for instrumentation applications also. Included is a summary of the market-specific RF front ends and the associated multi-market transceivers I've highlighted today. As you can see, there's a lot to choose from. I hope you've enjoyed this presentation.